invitation, Annalisa. It's a pleasure to be with you all, and Annalisa has given you a very good overview of what I've been doing since my alleged retirement. And I should say that throughout my career, on many occasions, I tended to steer away from what might be relevant from the development of the heart. But since my alleged retirement, as I'm going to show you, I've been very deeply involved with cardiac development. When I received this kind invitation initially from Christina and from Annalisa, they asked me to talk about the development of the heart. And I pointed out that in a session of 30 minutes, it would be exceedingly difficult to compress everything that we now know about development of the heart. So what I'm going to concentrate upon, as you see from the image on the screen at the moment, is remodeling of the embryonic interventricular communication. Because I do believe the evidence we now can find from the developing heart permits us to resolve ongoing controversies. I gather that you're not all necessarily immediately aware of the mysteries of the congenitally malformed heart, but there remain controversies between the way we look at things in Europe and the way that many people still view things in North America. And one of those controversies is the nature of the small chamber in the setting of double inlet left ventricle and tricuspid atresia. So I'm going to start off by showing you how we can resolve that controversy. I'm then going to continue and I'm going to show you that in the setting of double outlet right ventricle, when both arterial trunks arise from the right ventricle, surgeons often describe the channel between the ventricles as the ventricular septal defect. I think it's better considered an interventricular communication. So I'm going to show you how the surgeon repairing double outlet right ventricle does exactly the same as what the embryo does when remodeling the embryonic interventricular communication. And that is the reason why I think it is helpful now to distinguish between the channels that we might call ventricular septal defect as opposed to an interventricular communication. So why am I able to tell you all these things? Well, as Annalisa has explained to you, I retired quite some time ago now, allegedly, but I have been very busy. In that time, it's been my privilege to work with Tim Mohan, who is a excellent and expert developmental biologist in his own right. He initially worked at the Medical Research Institute at Mill Hill. When that transferred into the Crick Institute, the new institute in London, Tim came with them, and he's put together 450 data sets of developing mouse hearts. And he's examined these using the technique of what we call high-resolution episcopic microscopy. So I'm going to share with you a little bit of that information. Over the past 18 months or so, however, I've been working with Professor Wout Lammers, who initially was in Amsterdam. He's now at the University of Maastricht, where he works with Jill Hickspoors. And they have reconstructed a series of human embryos. And I'm going to show you some of this evidence. I also have evidence now from histologically serially sectioned embryos that are contained in the Human Developmental Biology resource, and that is housed in Newcastle. So I'm working very closely with my colleagues in Newcastle so as to make this material more generally available. I'm going to try to show you today how we can put all of this together. We can improve our knowledge of cardiac development, and we can directly relate that to what we see in the setting of the congenitally malformed heart. So this is one of the reconstructions that have been made by Jill and Wout from human embryos. I'm going to show you several pictures like this, and you'll see CS appearing all the time at the bottom of the slide. This stands for Carnegie Stage. And a long time ago now, in the early part of the 20th century, this system of staging was produced by investigators working at the Carnegie Institute in the United States. And the key stages for development are those that take place between Carnegie Stage 10. And as you see, this is an embryo from Carnegie Stage 10. It's being reconstructed by Jill and Wout. And this is about 4 weeks of development subsequent to conception. And then we're going to go on to Carnegie Stage 23. And that is 8 weeks of development. And that is the transition from the embryonic stage to the fetal stage. And as you will see, all the important changes take place during this stage of development. Now, the interesting thing to me is that at this early stage, it doesn't really look much like an embryo at all. You see that as yet, although we see the beginning of the head folds, the head hasn't tilted forward, as we expect to see in most of the embryos we look at. In fact, we've taken away the surface, the skin and the integuments of this particular embryo so that you can see that there is the heart. It's contained within its pericardial cavity. And there, emerging from the heart, you see the right aorta. In fact, the aorta is bilaterally symmetrical at this stage. You can also see there in gray, there is an extensive yolk sac. And on the yolk sac, there is a series of vitelline veins. They are colored in blue. Coming back and colored in purple, from the placenta, you see the umbilical vein. Now, the beauty of what Jill and Wout have done is that they have segmented all these parts so that you can take them away and you can look in and you can see what's going on within the embryo. So this is what is happening in that pericardial cavity. I've taken away the myocardium so that you can see the cavity itself. And you'll recognize that coming from the outside, you saw this in the previous image, in purple, you see the umbilical veins. In blue, you see the vitelline veins. And then as they approach the heart, they come together and they form the systemic venous tributaries. As yet, they're not draining any blood back from the embryo, but we'll see that developing in the fullness of time. At this early stage, about 4 weeks of development, the heart tube is a straight entity. But we know from lineage experiments that its larger part at this stage will become little more than the left ventricle. But already at its cranial end, it's beginning to expand a little, and that will eventually become the outflow tract. Arising from the outflow tract, and now you can see both of them, you see the aortas. Now, things happen very rapidly at this early stage. This is what we see at Carnegie Stage 10. We go from Carnegie Stage 10 to Carnegie Stage 11 in a single day. And again, I'm showing you what is happening to the cavity. We're looking at it from the front. But now we see the beginning of the key point for ventricular development, because that ventricular part is beginning to loop. And this is what we'll call the ventricular loop. And coming into it, at one end, we have the Atrioventricular Canal. Emerging from the other end, we have the outflow tract. So I'm now going to take you on another 2 stages. We've now moved from 29 days of development to about around 32 days of development. We've extended through 2 stages, so we're now at Carnegie Stage 13. Remember, CS stands for Carnegie Stage. And now you can see what has happened to that ventricular loop, because now you can see the beginning of formation of what is going to be the ventricular apical parts. You can also see that the whole thing is looking a little more like a heart. That is the Atrioventricular Canal. It's emerging from the atrial segment of the heart. You can already see that bulging forward from that atrial segment, we have the primordiums of the appendages, and they are going one to either side of the outflow tract. But from the ventricular loop itself, and what is called ballooning from the outer curvature of the ventricular loop, from its inlet part, we see ballooning of what will be the apical part of the left ventricle. From the outlet part of the loop, we have a further series of trabeculations, and they will form the right ventricle. Arising from the right ventricle, we have the outflow tract. So I've shown you the arrangement thus far as we see in these reconstructions that have been made by Jill and Wout from the embryos that are the original Carnegie collection. Now, the beauty to me is I can now correlate directly what I'm seeing in these reconstructions with the episcopic data sets that Tim Mohan has made of not only mice, but also human embryos. So we have a relatively limited series of human embryos. This is one that is now one stage further than the reconstruction I showed you just a moment ago, but it's a little different from what I've just shown you. So here you see a cut across the short axis of the developing ventricular loop in a human embryo, Carnegie stage 14. I've cut it so that you can see the base of the developing ventricles. You are standing at the apex, you're looking towards the base. So there you see the ventricular surface of the atrioventricular canal. Within the atrioventricular canal, you will recognize the atrioventricular cushions. And you can now very nicely see these developing trabeculations that eventually will be the left ventricle. And there now, for the first time, you see the interventricular communication. And what is clear, I hope, to you all, that all of the blood that is coming through the atrioventricular canal at this early stage of development has to pass through this interventricular communication. And that means we can never close the interventricular communication as we see it now. As the blood passes through the interventricular communication, it enters the developing right ventricle. And equally, at this early stage, you'll see, as I showed you in the reconstruction, the developing right ventricle is supporting the entirety of the outflow tract. So if I summarize what I can tell you at the moment and consider it in the setting of the morphology of that small chamber in the setting of double inlet left ventricle, which I've told you is still controversial, what I've shown you is that when we first see the embryonic interventricular communication, the embryo essentially has double inlet left ventricle, because all the blood from the right atrium, all the blood from the left atrium is entering that developing left ventricle. So if we look a little more carefully at the embryo at this stage, we can begin to get clues as to the nature of that second chamber. Because those who work still in parts of North America maintain that that second chamber is little more than an infundibulum. And indeed, if we go back to the old days, Helen Taussig, the mother of pediatric cardiology, called this entity an infundibular outlet chamber. Now, I got my own fingers very badly burned in the past when I tried to suggest that it was an outlet chamber. We can now do much better because we can look at the morphology of this second chamber in the light of what we see in the developing heart. So this is that self-same data set that I showed you, and the beauty of these episcopic data sets is that they are three-dimensional. So I can cut these data sets any way I want, as can the radiologists these days, as can the cardiologists who have three-dimensional data sets. I can change my cutting plane. And here I've taken what the echocardiographers call an oblique subcostal cut through that developing heart. So the cavity you see there is the cavity of the right atrium. And you see it has no connection whatsoever of what we see as this second chamber in the developing heart. You now see the en face view of that interventricular communication. And what we clearly see is that this second chamber, without question, is the developing right ventricle, because already it possesses what will become the apical component of the left ventricle. But at this initial stage, it's supporting the entirety of the outflow tract. But let's make comparisons now with what we see in postnatal congenital heart disease. And any of you who have experience with the pathology of the congenitally malformed heart will immediately recognize, I hope, that I'm showing you an example of what we call tricuspid atresia. And here you see the replica of that small chamber. There is the right atrium, as you saw it just a moment ago. It has no communication directly with the ventricular mass. And there now we see the developing apical component of the right ventricle, which is the apical component of the right ventricle in tricuspid atresia. There you see the interventricular communication. Now, of course, the outflow tract itself is separated. We're going to look at what happens to that outflow tract. And in tricuspid atresia, most usually it is the pulmonary trunk that arises from this small ventricle. And there is the aorta arising from the dominant left ventricle. But we know, as you see in this specimen prepared beautifully by my collaborator Diane Spicer, the essence of tricuspid atresia, as with the developing heart, is absence of the right atrioventricular connection. We are replicating an early part of normal human cardiac development. So what I can now say with certainty is that that small chamber in hearts having univentricular connection to a dominant left ventricle is the incomplete right ventricle. What I'm also going to show you, however, is that the infundibulum itself is not formed until much later in development. And that is what happens as we remodel the embryonic interventricular communication. And the first stage of that remodeling is to provide the right ventricle with its own inlet. And this is done by expanding the atrioventricular canal. So let's step back a couple of stages. And this is a cut through another of the episcopic data sets prepared by Tim Mohan, another human heart. Here we are back one stage, we're at Carnegie Stage 13. I told you at this early stage that the atrioventricular canal connects only to the developing left ventricle. And you can see that very beautifully in this section because there is the atrioventricular canal. And as you see, it is connected to the inlet part of the developing left ventricle. One stage later, and this is the embryonic data set I showed you just a moment ago from the human heart, there has been expansion of the atrioventricular canal. Those of you who are echocardiographers or have experience with echocardiography will immediately recognize right appendage, left appendage. You see again, we can see the atrioventricular canal at this early stage, and the atrioventricular canal has expanded, and by expansion, it's provided the right ventricle with its own inlet. Now, in fact, that expansion also sequestrates the atrioventricular canal myocardium itself as the vestibule of the developing atrial chambers. And that's also important, as we will see. But what we are concerned about at the moment is how this involves remodeling of the interventricular communication. And this is some work we did quite some time ago now. In fact, we did this work in 1990, again with colleagues of mine who were working in Amsterdam, because we were fortunate that we were able to serially section human embryos And we were able to stain them with an antibody to the nodose ganglion of the chick. And this was serendipity, but that antibody marked the embryonic interventricular communication. You should now be able to relate this to the images I've already shown you, because you can see the atrioventricular canal connected exclusively to the left ventricle. But there are these cells marked by the nodose ganglion to the chick, and as you will see, they encircle the primary interventricular communication. But those cells are also part of the right half of the atrioventricular junction. And what I've shown you is that the right atrium gains its access to the right ventricle simply by expanding the right atrioventricular junction. And by tracing the fate of this ring of cells, we were able to show that that was exactly what happened. It is remodeling of the dorsal part of the embryonic interventricular communication that provides the right ventricle with its own inlet. Because you see that the ring has expanded, giving the right ventricle its own inlet, but there is the retaining part of the ring. And now we can see that there is a second interventricular communication, because the dorsal part has encircled the inlet to the right ventricle. So now I'm not just going to call it the interventricular communication, I'm going to call it the second interventricular communication. And I've shown you that expansion of the primary foramen has brought the cavity of the right atrium into communication with the developing right ventricle. I've also shown you that the atrioventricular canal myocardium itself is going to become the vestibules of the right and left atrial chambers. But you will appreciate, I hope, that although the dorsal part of the foramen has expanded, the ventral part has not. And that is because at this early stage, the embryo is replicating what we see in later life as double outlet right ventricle. So now I'm changing. I'm showing you data sets of what happens in the mouse heart. One of the problems with looking at data sets in the human heart is that the heart remains full of blood. With these mouse embryos, we can wash out the blood, we can fix them, and we can see much better as to what is going on. Again, it's an oblique subcostal cut, but already now you see that the atrioventricular canal has expanded, so the right ventricle has developed its own inlet. And now there is that channel between the ventricles, and we can call it the second foramen. But you also see the pulmonary root, the aortic root, are still carried above the cavity of the right ventricle. So how does the aortic root become committed to the left ventricle? And it all depends on what happens to these structures. And these structures are the proximal end of the two cushions that are dividing the outflow tract into its aortic and pulmonary components. And they are going to do what the surgeon does when correcting double outlet right ventricle. They are going to build a shelf in the roof of the right ventricle, and they are going to commit the aortic root to the left ventricle. So this happens at embryonic day 12.5 in the mouse, Carnegie stage 16 in the human, about 5 weeks of development. By that stage, the distal cushions have already separated the distal outflow tract into the aortic and pulmonary roots. But as yet, the proximal cushions have not formed that shelf. By creating the shelf, they will tunnel the aortic root into the left ventricle. And we can see that process now as it happens by looking at a large series of these serially sectioned embryos from mouse development. So this, in fact, is the data set I showed you just a moment ago. That is the right ventricle. There is the aortic root. The aortic root and the pulmonary root unequivocally are arising from the right ventricle. But you can see now that the atrioventricular canal has expanded, and that is the remodeled dorsal part of the interventricular communication. And you've seen again that we now describe the channel between the chambers as the secondary communication. But when I take my cut a little more anteriorly through this data set, I can show you how the mouse is fusing together the parietal cushion, the septal cushion. They fuse together and they create this shelf in the roof of the right ventricle. The aortic root is still positioned above the developing right ventricle, but by creating this shelf, the embryo has created this tunnel that puts the aortic root into the left ventricle, converting the secondary foramen into the outflow tract for the left ventricle. So prior to construction of that shelf, the heart had double outlet right ventricle. As I've emphasized now several times, the surgeon builds a shelf to tunnel the aortic root to the left ventricle, the setting of double outlet, and so does the embryo, so that the secondary interventricular communication becomes the outflow tract for the left ventricle. So this is a specimen of double outlet right ventricle, again photographed beautifully by Diane Spicer. So there you see the right ventricle, and there the aortic root. There's the pulmonary root, both arising from the right ventricle, and that is what we call the outlet septum. So there is the channel between the ventricles, and you will immediately appreciate we cannot close that hole, and that is why we should not call it a ventricular septal defect, because that area is the area closed or tunneled by the surgeon so as to put that interventricular communication in communication with the aortic root as the outflow tract for the left ventricle. Should we describe it as a ventricular septal defect? Well, let's make an analogy with tetralogy of Fallot. This is another of Diane's beautiful images, and it shows you the cut through the aortic root in the setting of tetralogy of Fallot. You will appreciate, I hope, that the aortic root overrides the crest of the ventricular septum in the setting of tetralogy. So there is a cone of space beneath the overriding aortic root, and it has a left ventricular end, it has a right ventricular end. Which does the embryo close to put the aortic root back into the left ventricle? Exactly the same as the surgeon. It is the right ventricular entrance that is closed. And in fact, we can parallel tetralogy by looking at the developing heart. This is another of the murine hearts. And there now you see the secondary foramen, and there is the channel that is going to be closed. It's an aortoventricular communication. So the building of that shelf has remodeled the secondary foramen to become the outflow tract, leaving a channel between the aortic root and the right ventricle. So now I can call that the tertiary foramen, and it is that tertiary foramen that is eventually closed to complete septation. And we can see how the mouse does it, and the human does exactly the same thing. So I've rotated the data set now. So you're standing at the apex of the ventricles, and you're looking towards the ventricular base again. To beneath, you see the left ventricle, the ventricular septum, and there you see the subpulmonary outflow tract, and that is the end of those cushions that have formed this shelf in the roof of the ventricle. There is still a communication at this stage. It's an aortoventricular communication. And that is what is going to be closed by these tubercles of the atrioventricular cushions. A different view showing you the aortic root. There are the tubercles. They are closing the embryonic interventricular communication, and the proximal cushions themselves will muscularize to form the infundibulum, and it is those tubercles of the cushions that will become the membranous septum. Note that I've also shown you the buttress of the atrial septum. That is the true second atrial septum, and that is formed as an atrial structure. So what I've shown you, the proximal cushions have created the shelf. They have replicated what the surgeon does. The embryo closes the aortoventricular communication. The surgeon corrects double outlet right ventricle. Those tubercles will form the membranous septum, and exactly the same thing happens in the human embryo. So I've told you that I also have access to the serially sectioned human embryos from the Human Developmental Biology Resource. This is an embryo close to the end of the period of development, Carnegie Stage 22. We're nearly now at 8 weeks of development. It's a 4-chamber section again, and there you see the aortic root, and that is the tunnel that connects the aorta to the left ventricle. If I take my section a little bit more anteriorly, you can see that tunnel. It's between the pulmonary root and the right ventricle. There it is. And now this shows you those tubercles of the atrioventricular cushions that in the human heart, just as in the mouse heart, are forming what will be the membranous part of the ventricular septum. And so, if I summarize everything that I've told you, the dorsal part of that primary embryonic interventricular communication remodeled to become the right atrioventricular junction surrounding the tricuspid valve. The second part became the outflow tract for the left ventricle, and it is the tertiary interventricular communication that is closed by those tubercles of the atrioventricular cushions that become the membranous septum. And if it doesn't close, we have a perimembranous ventricular septal defect. And in fact, Dr. Mohan also did a series of data sets in which he had perturbed the furin enzyme. And for reasons we cannot fully understand, one of these mice persisted with what we can recognize as being equivalent to a perimembranous ventricular septal defect. So this is a cut through that mouse, and we can see how the secondary interventricular communication is now the ventricular outflow tract. And there is persistence of that channel, the tertiary foramen, which has not closed. You see in this particular mouse, the inner heart curvature still separates the developing aortic valve from the developing tricuspid valve. But there in the dorsal margin of the foramen, we see fibrous continuity between the developing tricuspid and mitral valves. And now we can relate this knowledge that we have gained from the appreciation of normal development to the pathologic specimens and to clinical experience. Because this is another of Diane Spicer's beautiful pictures showing you the left ventricular view of a perimembranous ventricular septal defect. We used to think the phenotypic feature of this lesion was fibrous continuity between the leaflets of the aortic and tricuspid valves. But just as in that mouse, in this human heart with a perimembranous defect, we see that there is discontinuity between the aortic and tricuspid valves, but still continuity between the tricuspid and mitral valves. So we have to modify our definitions as more and more evidence becomes available to us, but of particular importance, we can now relate this new development to what we see happening during development. So in this short period we've had available today, I've tried to show you how remodeling of the embryonic interventricular communication knowledge of those processes sets the scene for understanding what we see in the setting of congenital cardiac disease. I've taken one particular instance here, remodeling of the embryonic interventricular communication, but the availability of those data sets prepared by Wout Lammers and Jill Hicksbos now relate to the entirety of the understanding of the congenitally malformed heart. So there you see my final slide. Current knowledge of ventricular septal defect does now permit us to provide a realistic interpretation of what you as pathologists see when the heart is congenitally malformed, but not only for the interventricular communication, but for the entirety of cardiac development. So thank you very much for permitting me to be with you today, to share this, what I think is fascinating information, because we are just scratching the surface at the moment. There is so much more still to come, but it's all very exciting. And so hopefully you have appreciated what I've told you. So thank you for permitting me to be with you.